record this. I'm going to record this session, so you guys will be able to review it later. And if there may be some more people coming, and if not, then they can watch the video as well. So glad to have you all here, guys. Thanks for coming in. I hope you're all staying well, staying healthy, and getting used to this whole virtual teaching format that we've been dealing with now for the last couple of weeks anyway. What we're going to do today is we're going to finish chapter 7, actually. And actually, that's the last chapter on linear algebra. So by the end of the next 2 hours, we're going to be going back to differential equations again. I forgot to sort of give you that cliffhanger on Tuesday. But yes, we have done a lot of linear algebra for quite a few weeks, and we're ready to spend the last month going back to differential equations and looking at how linear algebra can help us to solve differential equations that we couldn't do before. So we're going to finish chapter 7, and then we'll take a break as usual somewhere in the middle of class. I'm going to give you a chance to ask questions about the homework that is due today. I did create a Dropbox folder, and I shared that through email with you guys. You should have received an email to deposit your homework, which is due by tonight. But I'll take questions on that if there are any later on in the class. And then we have some group work that was kind of left over from Tuesday, and then sort of a new group work for today based on what I'm going to talk about right now that I think we could also look at. So quite a bit that we're going to be able to get done today. We're making great progress, guys. We're doing fine. I know it's been a headache, this transition, but we've managed to do pretty well in terms of keeping up with the material and everything. So like I always do, I've got a recap here on the board behind me. The part that's in the lower right corner in blue is just a reminder about an example that we had done on Tuesday, because I'm going to come back to that example today. And I just wanted to keep the key elements of that example on the board for you. But the main recap up here in black, remember we're working with square matrices, and we're trying to find eigenvalues and eigenvectors for this square matrix. Okay, so I will call those eigenpairs, and there's a lambda and a v, and they sort of go together as a pair, the eigenvalue and the eigenvector. The absolute crucial equation that relates the lambda and the v in this situation is this one right here in the box, AV equals lambda v. And you actually need that equation for some of the homework that you're doing for today, because I gave you a few theoretical problems to work on for today's homework assignment. So anyway, so we'll be coming back to this equation quite a bit today. But when you're actually trying to find the eigenvalues and eigenvectors, there's a more computational approach to that, right? For the eigenvalues, we simply have to solve this characteristic equation. The determinant of A minus lambda I equals 0. So you're going to basically subtract lambda from the main diagonal of the matrix A. And that gives you a matrix. You can write down the determinant of that matrix and solve for the lambdas. This is how you get the eigenvalues of a matrix. Okay? Once you have the eigenvalues, you can then proceed to find all of the eigenvectors. And they actually form what's called an eigenspace. I wrote the notation E sub lambda here. The eigenspace corresponding to lambda is just the null space of A minus lambda I. So you actually have to do a whole null space calculation with this matrix. And because your matrix is not invertible, you see that here, the determinant is 0. So because your matrix is not invertible, then this null space will not be trivial, right? You'll be able to come up with some interesting vectors in that eigenspace, in that null space. Okay? So this is just a review from Tuesday. How do you find the eigenvalues and eigenvectors of a matrix? Okay? Is everybody good so far? I'm just going to remind you that, as usual, you're certainly welcome to speak up if there's any question. Just unmute yourself. You should be muted, I assume. But feel free to unmute yourself if there's any question as we're going along. You know, I want this to be interactive if possible. So let me know. Does everybody feel good about the procedure so far? Great, great. Okay, so I'm seeing some good signs out there. This is what you're going to primarily be doing for next Tuesday's homework. The homework that you're doing for today, which is a very short assignment, really is more focused on the theoretical relationship, AV equals lambda V. So the solutions tend to be pretty short. You don't have to write out a whole lot. But for next Tuesday, you do have a much longer homework assignment. I will definitely encourage you to start early because you're going to be actually going through the eigenvalue, eigenvector procedure on a number of examples. Okay, so you have to find determinants, you have to find null spaces, and so on and so forth. Okay. One last thing I want to remind you about before we go on. It's so critical that you get the lambdas correct, right? That you actually solve this characteristic equation correctly. It's so critical that I wanted to share with you, and I did on Tuesday, these fun facts at the top, because the fun facts are a great way of just checking to make sure that you got your lambdas correct, or at least give you some confidence that you probably got them correct. If you add up all of your lambdas, you get the trace of your matrix, right? And if you multiply all of your lambdas, you get the determinant of your matrix. So if you take your matrix A, you can always find the trace. The trace is just the sum of the main diagonal, right? You just add up the numbers on the main diagonal. It's very easy to figure that out. Your lambdas should add up to that trace. And you can also very easily find the determinant of your matrix and make sure that your lambdas multiply to that determinant, right? So these fun facts are nothing that I proved, but they're very helpful for making sure that you got your lambdas correct. So I want that information. Okay? Great. What I think I'd like to do next, so I've got one example that we did on Tuesday, sort of recapped here on the bottom right corner of the board. I'd like to practice on one more example right now and say a few more things about this. And we're going to see in this next example kind of a difference from the example that we did on Tuesday over here in the bottom right. So let's start a new example. Do a new example here. So here is the example. Let's find bases. Let's find bases for the eigenspaces of, I guess I'll call this matrix B just to distinguish it. I want to use a different letter for this one. So the matrix B is going to be 2, -5, 5, 0, 3, -1, and 0, -1, 3. Okay, so let's take this matrix here and let's just run through the whole procedure one more time, okay? The same way we did a few examples on Tuesday. Okay, so what I'm going to do for this solution, remember that you have to start by finding the eigenvalues. So let me start with that, okay? I'm going to take the determinant of the matrix that I get when I subtract lambda from the main diagonal. So this is just B minus lambda I. So I'm just subtracting lambda off of the main diagonal. All of the rest of the numbers stay exactly the same. Okay, so there's my determinant. Okay. By the way, I have a quick comment for you guys that I did not make on Tuesday. Some of you might be wondering whether you can take your matrix at the beginning and right off the top do EROs to it. And maybe it'd be easier to get the lambdas or just to solve the problem, right? By doing EROs. It turns out, guys, that in this chapter, you cannot really do EROs. And the reason that you can't row reduce anything about your matrix is that it's not really this matrix B that you're concerned with, is it? It's this one right here. This is the matrix that you would need to manipulate with elementary row operations if you wanted to, for example, simplify the determinant. The problem with this is that because this matrix has the lambdas in it everywhere, right? You see the lambda variable everywhere. It gets very difficult to sort of add multiples of one row to another row because these lambdas are sort of flying all over the place. So this gets to be a little bit of a problem.
Yeah.
Okay, again, if you're watching, you can keep your mics muted unless you have a question. If you have a question, feel free to unmute yourself and let me know. Okay, I just muted everybody again. You should be able to unmute yourself if you need to, but just try to keep the background quiet or use headphones is the other way to do it. Okay, great. Hopefully I'm coming through okay for everybody so far. So what I was just saying is that you cannot really do EROs on this matrix very well because you have this lambda variable that is inside the matrix, right? I mean, you know, for example, you know, how are you going to add a multiple of like the second row to the third row? It's just going to create a crazy expressions involving the lambdas. So try not to do that. Try not to be tempted here to use EROs. We're just going to have to sort of rough it and just do the determinant of this matrix. Now, fortunately, this matrix has a very nice column. The first column has a lot of zeros in it. So we can expand on that first column. Remember on Tuesday, I mentioned that it's not a good idea to use the arrow method most of the time. Occasionally you can get lucky with that, but it's usually not a good idea to use the arrow method on these matrices because you're not going to get your characteristic equation nicely factored in that case. So in order to get a nice factorization of your characteristic equation, it's actually going to be best to expand along a row or a column. So Matt's got a question here in the Zoom chat. It's not that it's wrong to use the arrow method or to use some other determinant tricks that we might have learned. It's not wrong to do those things, but my point is that in terms of the tools that we have, the one that works the best for finding eigenvalues is this cofactor expansion method, at least for 3x3 or larger matrices. If you have a 2x2 matrix, it's very easy to just use the AD minus BC formula. That's okay for a 2x2. But for a 3x3 matrix, I highly recommend using the cofactor expansion method. There are a few problems in the homework that you're going to be doing for next week where the matrix doesn't have any zeros in it at all. It's like a 3x3 matrix that has no zeros in it at all. And you're probably wondering, well, how am I going to do that? If we're not supposed to do EROs and we have no zeros in the matrix, the cofactor expansion is going to be messy. Like, what are we supposed to do? Well, the thing is, on some of those homework problems, they just give you the lambda values sort of for free. Sometimes I'll do that. Even on an exam, sometimes I'll just, to take all of the guessing game out of it, that you're going to get those lambdas right. Sometimes I'll just give you the lambdas because I want to make sure you have them right. It is so important to have them right. Or maybe I might also give you 2 out of the 3 lambdas. And then I would ask you to figure out the third one by using the fun facts. Right? So you could, for example, find the trace of your matrix, take the 2 lambdas that I gave you for free, and subtract them over to figure out the third lambda. that's another little trick that sometimes comes up. Okay, so anyway, there's all sorts of tricks, but generally the go-to foolproof way of finding your lambdas is to cofactor expand. So I'm going to do that right here. I'm going to expand the first column in this case. Remember, it's not always the first column or the first row. It could be anything. But when I do that, I have 2 minus lambda from the upper left corner times, I'm going to use larger brackets now, this little 2 by 2 submatrix. So this is 3 minus lambda times 3 minus lambda, and then minus 1. Okay, and now I'm going to not multiply it all the way out. Don't do that because you'll end up with a cubic that's hard to factor. Leave it factored. Leave the 2 minus lambda on the outside. The part in brackets, we can multiply this part out. It doesn't factor because there's a minus sign here, but we can multiply this part out because it's only going to be a quadratic, right? So we're going to get lambda squared minus 6 lambda plus 8. Okay, if I actually multiply that out, and then that does factor. We have 2 minus lambda already outside, and then we have lambda minus 2 times lambda minus 4. Okay, so it factors pretty good. And so my lambda values, remember that you're going to set this to 0. So your lambdas are 2, 2, and 4. Okay, those are your lambdas. In a second, guys, I'm going to erase the left side of the board, so make sure you get this copied. I do want to just note that we can check these lambdas with our fun facts, right? If we add up our 3 lambdas, 2, 2, and 4, we get 8, which, what is the trace of the matrix B up here? 2 plus 3, which is 8, right? So these lambdas satisfy that fun fact. And if you take the determinant of the original matrix by using, cofactor expansion along the first column, you will get 16, which is 2 times 4. Okay, so the lambdas are consistent with the fun facts. It seems like it's most likely correct. Okay. Everybody good so far? All right, so I'm hoping everybody's had a chance to copy this down. I'm going to erase this now. One last thing. If lambdas are being repeated like you see here, you want to make sure you write down the repeats. So the lambda repeated 2 times, I write it down 2 times. Just like over here, in this example, the lambda equals 3 showed up 2 times, so I wrote it down 2 times. Okay, so there we go. We've got our lambdas. Let me come back here. I'm going to erase this now and work on the corresponding eigenvectors. When you have an eigenvalue that repeats, so when you have an eigenvalue that repeats, you want to actually always look at that one first. Okay, and I'm going to explain in just a few minutes why that is. Okay, so the repeated eigenvalue in this case was lambda equals 2. So what we do is we now look at the null space of the matrix that we get when we subtract 2 from the main diagonal. So I'm subtracting 2 because remember, it's A minus lambda I, right? A minus lambda I. So I'm subtracting 2 times the identity matrix, and this is what I'm getting. I'm getting this matrix right here. Remember, as I said on Tuesday, this matrix cannot be invertible, right? And you can see that it's not. Actually, you can see that all 3 rows of that matrix are multiples of each other. So if you want, you can cross off 2 of them because they're all really just multiples of any one of them. I'm just going to cross off the first one and the third one. Doesn't really matter necessarily which one you do, but I have a pivot right here. Okay, so if I think about x, y, and z, notice that z is a free variable. I'll call it t. And then from the middle equation here, y minus z equals 0. So that tells me that y is also going to equal to t, right? So y minus z is 0. And notice that x, this is kind of interesting. The column that goes with x has all zeros in it. And I see students sometimes make the mistake that they think that means that x is 0. But actually, the fact that we have a column of zeros there means that there's no pivot in that column. That means that x is also free. So I'm going to give it a different letter. I'll call it r. So x and z are free variables. And then we solved for y in terms of that. Okay. Hopefully so far so good. So my null space, you know, if I was building vectors out of this null space, it would look like this. Those are my Eigenspace vectors, right? So if I want a basis, because the question was asking for a basis for E sub lambda equals 2, it's always best to just give a basis, guys. Giving a basis is the best way to answer these questions, right? Because a basis explains everything that you need. So a basis, if I bust out the R, I get 1, 0, 0. And if I bust out the T, I get 0, 1, 1. So this is actually a two-dimensional eigenspace, right? I've got two vectors here in that eigenspace. So that's pretty good. All right? That's different than what happened over here, right? Did you notice on the previous example that we did on Tuesday? We had the same lambda twice, but we only got one eigenvector out of it. Okay, so this is actually something that I'm going to come back to in just a second. Okay, the other eigenvalue here was lambda equals 4. That was our second eigenvalue. I'm going to skip the details for this one. Again, you just have to subtract 4 from the main diagonal of B and then row reduce it. I'll let you guys check it. I'm just going to write down the answer without writing out all the work. So a basis for that eigenspace, so just take my word for this one, it just comes out to be 5, -1, 1. Okay, so you guys can check that one on your own. I won't go through all the details of the null space again on that, but it's the same procedure. Okay? So there's a reason that I wanted to have these two examples side by side with each other. Because both of these matrices are 3 by 3. They both gave us 3 lambdas. Again, I have to count the repeats, right? So this was 3, 3, and 1. That's 3 lambdas. Over here, we had eigenvalues 2, 2, and 4, which is 3 lambdas. So these are both 3 by 3 matrices. They both give us 3 lambdas, but look at the difference. Look at the difference in the eigenvectors. In the first matrix over here, we only got 2. We got 1 for each of the lambdas. But in the second example, we actually got 3 eigenvectors. If you collect all of them together that we found, there are 3 eigenvectors here. And that's because this eigenvalue lambda equals 2 actually gave us 2 eigenvectors. So Caesar is asking a question if this is how we would like to write the basis. This is absolutely yes. The answer to your question, Caesar, is yes. This is exactly how I would love for you to write your answers to these kinds of problems. Absolutely. Okay. So do you see the difference? So there's actually a definition associated with this, which I want to write down for you now. So I'm going to come up here and we're going to make a definition. So this is a very, very important concept, as it turns out. So I want to make sure that I spell this out real carefully for you. Okay, so an n by n matrix with n linearly independent eigenvectors, okay, is called non-defective. Okay, so a non-defective matrix is one that has n linearly independent eigenvectors. It turns out there's another name that we sometimes give for this, which will make more sense in just a little while. We will sometimes say that this matrix is diagonalizable. That's kind of a fancy math word. You'll understand shortly why we call it diagonalizable. So if we have a matrix with n linearly independent eigenvectors, it's going to be called non-defective or diagonalizable. Otherwise, of course, the matrix is defective. Okay, so we have this concept of defective and non-defective. So that's a concept that you're going to see in the homework that you're going to do for next Tuesday. I'll just make a note. In our examples, A is defective, but B is non-defective, right? A is defective, but B is not defective in our examples that we've just been practicing on. Look at the matrix A. It's 3 by 3, but it only gave us 2 linearly independent eigenvectors here. But the matrix B over here, which is also 3 by 3, did give us, right, we see it here, it did give us 3 eigenvectors, right? So it turns out that what's really going on here is that when an eigenvalue repeats, which actually happened in both of my examples, right? There was the same eigenvalue more than once. When an eigenvalue repeats, it might not pull its weight. This is the way I'm going to be saying it. It might not pull its weight. Look at lambda equals 3. It has a weight of 2. In other words, it showed up twice as a root of the characteristic equation. It has a weight of 2, and it didn't pull its weight because it only gave me 1 eigenvector, right? 1 linearly independent eigenvector. In this example, matrix B, lambda equals 2 also had a weight of 2, but it did pull its weight, right? So even though the eigenvalue showed up twice, we got 2 eigenvectors out of it, so we were happy, right? So B was non-defective because every eigenvalue pulled its weight. In fact, this is a fact that I should write down for your notes, because this is really what it comes down to. What does it really boil down to when we're asking about whether a matrix is defective or not? So this is the key fact. The key fact is a matrix is non-defective if and only if non-defective, right? This says non-defective here. I hope everybody can read my board okay today. Sometimes the lighting can be tricky. A matrix is non-defective if and only if every eigenvalue pulls its weight. I'm going to explain what that means. Yeah, that's kind of this is kind of my sort of slang way of saying it. Every eigenvalue has to pull its weight. So in other words, what this means is, so i.e. m sub lambda, this is sometimes called the multiplicity of lambda, the multiplicity of lambda is equal to the dimension of the corresponding eigenspace. This is really what, when I say that the eigenvalue pulls its weight, I'm really just saying that its multiplicity equals the dimension of the eigenspace. Right, so over here in this matrix A, the multiplicity of 3 was 2, right? Lambda equals 3 shows up 2 times as an eigenvalue, but the dimension of the eigenspace, we only have one basis vector. It means it's one dimensional, right? So in that case, the eigenvalue failed to pull its weight. Now, you might be wondering, okay, well, if one of my eigenvalues fails to pull its weight, would it be possible for another eigenvalue to overpull its weight and make up for the deficiency of the other eigenvalue? In other words, if one eigenvalue fails to pull its weight, can another eigenvalue rescue it and overpull its weight so that at the end of the day, you still get your n linearly independent eigenvectors? The answer is no, that cannot happen. No eigenvalue will ever be able to overpull its weight. So like on this example here, lambda equals 3 failed to pull its weight. You might be wondering, could this other lambda over here, lambda equals 1, could it overpull its weight and make up the difference for what this eigenvalue fell short? The answer is no. And you can see this eigenvalue, lambda equals 1, did not pull any more than what its weight was, which was a weight of 1, right? So this is a fact that usually gets proven, say, in like a 300 level math class on linear algebra, that no eigenvalue can ever overpull its weight. What that means is that if somebody asks you if a matrix is defective or non-defective, you should run right away to the repeat eigenvalues first. You should look at those first because those are the ones that might not pull their weight. You notice when I did this example on Tuesday with lambda equals 3, 3, and 1, I did lambda equals 3 first, right? And on the matrix B that was just over here a few minutes ago, I did the repeated eigenvalue first. Why? Because the repeated eigenvalue is the one that might mess us up, right? It might not pull its weight. So I check those repeated eigenvalues first. If they don't pull their weight, the matrix is defective. The other eigenvalues are not going to be able to overpull their weight and make up for the difference, okay? By the way, any eigenvalue that has a weight of 1 is going to be perfectly safe, right? So like over here, lambda equals 1. Of course, every eigenvalue has to at least produce 1 eigenvector. So I'm not worried about eigenvalues that only have a weight of 1. If I have distinct lambdas, different lambdas that are not repeating, everything's going to be cool. It's only when we get these repeat lambdas that we might have a situation where the eigenvalue doesn't pull its weight. And if that happens, then the matrix is defective for sure. Okay, I hope this makes sense. So when you're working on these problems and you see an eigenvalue that gets repeated, you want to attack that one first. You want to see whether that eigenvalue pulls their weight first. And if it does, great, then you can continue to the other eigenvalues. Okay. Any questions? Everybody kind of got the idea there on that? Okay. The one thing I haven't really done with you guys though so far is I have not really explained what this is good for or why anybody should care. Why do we care if what's so great about having a non-defective matrix as opposed to a defective one? Like why does that make any difference at all? So I'm going to erase on the left side and start trying to answer that question for you. The main thing that we can do with a non-defective matrix that we can't do with a defective one is diagonalize that matrix. I have this other word over here, diagonalizable. A non-defective matrix is diagonalizable. I want to explain what that means and why it's important, okay? So this is actually section 7.3. So let me get a marker here that's a little better. 7.3, this is called diagonalization. I want to show you why it's nice if you have a matrix that is non-defective. Okay, I'm going to show you what this is good for. So let's let capital A be n by n. I'll just write it like that. Be non-defective. Suppose it's non-defective now. Okay, so again, that just means that every eigenvalue pulls its weight, and we can find, you know, we can find n linearly independent eigenvectors. That's all that this means right now. Okay, what's so great about that? This is the question. Okay, so let's do this. Let's consider for this matrix, let's consider n linearly independent eigenvectors. I'm going to write them as v1, v2, dot, 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 dot. Okay, all the way up to, let's say it goes up to vn. And these eigenvectors correspond to, you know, some lambdas. Let's say lambda 1, lambda 2, all the way up to lambda n. Now, some of those lambdas could be repeats. There's nothing wrong with having a repeated lambda as long as that repeat pulled its weight and gave us the corresponding number of eigenvectors. So please don't assume that these lambdas are all different. They don't have to be. Like the matrix B that we did a few minutes ago, we had a non-defective matrix, but we had eigenvalues 2, 2, and 4. So there was a repeat there, right? Okay, so let's suppose we have this setup. What we are going to do is we are going to form a matrix which I'm going to call S. Okay, and this is the same notation as it is in the book. And this is going to be made up of the columns consisting of these eigenvectors. So just lay these eigenvectors into the columns of a matrix. I want you to notice that this is going to be an n by n matrix. Obviously, there are n columns here, and each one of my eigenvectors is a vector in Rn, right? And I can write it as a column. So I end up with an n by n matrix. It's a square size, right? S is a square size matrix. Actually, it's even better than that. S is actually invertible. Let's think about why is that true. This goes back sort of before spring break, I guess. Why is S invertible? Well, look at its columns. Its columns are all linearly independent, right? One of the things that we learned in that, remember that invertible matrix theorem that has parts A, B, C, D, E, F, G, all the way down to like P or something? One of the statements in the invertible matrix theorem was that a matrix is invertible if it has linearly independent columns. So that's exactly what S is. It's a matrix whose columns are the linearly independent eigenvectors. So let's suppose that we have a non-defective matrix, and then we can do this, right? We can just throw those eigenvectors, those linearly independent eigenvectors, into the columns of this matrix. Okay, and what I'm going to do now is I'm going to come over to the other side, and I'm going to do a really cool little calculation, which is going to show you something about diagonalization. So I guess let me just make a quick note here. The note is that S is invertible. S is invertible, and this is just since it has Li columns. Its columns are Li. So because S has linearly independent columns, it's invertible. We're actually going to see the S inverse matrix show up here in a minute on the right side. So I just wanted to make sure that everybody understands that is an invertible matrix. Okay, so I'm going to do something here. I'm going to do a calculation. I'm going to calculate A times S. Just going to see what we get. All right, so that's just A times the matrix V1, V2, dot, dot, dot. I'm laying out the matrix S in column by column format. Okay, just putting in what S is. And now, of course, when I actually do this multiplication, so I'm multiplying two matrices together here. Everybody hopefully remembers how to do that, right? We go across the rows of the first, the rows of the first matrix and down the columns of the second matrix. So go like this and do those dot products, right? So in this case, what happens is you end up just getting a new matrix that has AV1 in the first column, AV2 in the second column, and on and on and on, AVN in the last column. So you just get those columns like that. And those expressions should look familiar in this chapter. Remember the most important equation in chapter 7, the one we started with. AV equals lambda V. So I can replace right here, I can replace AV1 with lambda 1 V1. And I can replace AV2 with lambda 2 V2, dot, 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 dot. The last column will be lambda n Vn. And what you have there, guys, is you have a matrix where the columns of S have been multiplied by the different lambdas. Sorry, I'm in the way of your of your screen here, right? So I've taken the matrix S and I've multiplied the columns by these different lambdas. Well, there's a way to do that with just a matrix multiplication. What you can do, I'm going to do another equal sign. What you can do is you can actually just take the original matrix, so V1, V2, this is the original matrix S. Okay, just take all of those eigenvectors that are listed in those columns, and you can multiply on the right by this matrix that I'm writing down right now. Lambda 1, lambda 2, all the way down the main diagonal to lambda n with zeros everywhere else. Okay, so this is what you can do. Let me make sure that you believe that. Okay, so for example, if I had a matrix A, B, C, D, and I multiplied it on the right by 5, 0, 0, 7, right? What would you get? Well, if you just multiply this out using your usual matrix multiplication, you'll get 5A, 7B, 5C, 7D. You see, when you write multiply by a diagonal matrix, a matrix that's just got numbers only on the main diagonal, you end up multiplying the columns of the original matrix by those respective numbers. This is always going to work. So that's exactly what I did in this last step right here. I said, look, all of my columns are being multiplied by these various lambda scalars. Let me make a diagonal matrix out of those lambda scalars and extract that matrix to the right and leave S on the left. See, what do you actually have here now? You actually have S on the left being multiplied by what I'm going to call D, right? So D is just this matrix, this is just where D is just the matrix that has those lambdas going right down the main diagonal. Lambda 1, lambda 2, dot, 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 down to lambda n. This is a diagonal matrix. This is why it's called diagonalization, because there is a diagonal matrix that is involved in this process. Okay? Again, slow me down. If there's any question, feel free to ask. You can unmute yourself or you can ask in the Zoom chat, either way, if I'm going too fast or if anything's not clear. But what does this note say? In summary, AS is equal to SD. That's really what we ended up showing. And this is usually written slightly differently. Namely, we will usually pull the S inverse. So what we will do is left multiply. We will left multiply by the S inverse on both sides of the equation. And there in that box is the equation that you really want to know. Okay. Remember, I already said that S is invertible. So putting the S inverse here is a perfectly safe thing to do. Okay. Perfectly safe thing to do. So far, so good? You could also, if you prefer, you could solve it for, instead of solving for S inverse AS equals D, you could solve for A. See, what would that be? That would require me to right multiply by S inverse. So I would have my equation solved that way around. Now, it is important that you get the S and the S inverse on the correct side of the equation, right? So when you're learning these formulas, make sure that you get the inverse matrix in the correct position relative to the matrix, okay? So I want to make a couple of comments here, and then we will be in pretty good shape. I might do an example or two as well, but couple of comments about this. The first one is, in fact, maybe I should write some remarks. This is worth putting into the notes. So let me try to write some things down over here. So some remarks. Okay, the first remark, guys, is that you cannot cancel the S with the S inverse in either of these equations. And you also cannot cancel the S up here. Be very careful about that, right? We do know that S times S inverse would equal the identity. That's true. But if there's another matrix in between the S and the S inverse, we cannot cancel. Remember that the order of the matrices in the multiplication cannot be changed. So if the S and the S inverse are not right next to each other, they cannot be canceled. So let me just write that down. We cannot cancel S or S inverse here. Okay, we have to leave it exactly as we see it in that equation. Okay, we can't cancel. The second remark is that if we take the determinant, this is actually kind of cool. Okay, if we actually look at the determinant of A, so using this bottom equation, we see that it's just the determinant of S d S inverse. And I'm sure you guys remember that determinants respect multiplication. So it's the determinant of S times the determinant of D times the determinant of S inverse. I'm sorry, that's an S inverse. I had to squeeze that onto the right side of this board here. I was running out of room. Let me try one more time to write that a little bit better. I think I can squeeze this in here a little bit nicer. Determinant of S inverse, like that. Okay, I hope everybody can see that, all right? Now, here, guys, these are three numbers. With numbers, of course, the order in which numbers are multiplied together makes no difference. And so, for example, we learned back in chapter 3 that the determinant of S is the reciprocal of the determinant of S inverse. Remember that? So you can actually cancel. Now you can cancel. I can't cancel over here, but I can cancel these two numbers here, and just write determinant of D. Right? So I canceled the determinant of S with the determinant of S inverse. And remember what D was. I've already erased it. This is the problem with having this small, tiny board. The matrix D, it should be in your notes, it's just a diagonal matrix. And you probably remember that the determinant of a diagonal matrix is just the product of the diagonal entries. So what is that? Well, that's lambda 1, lambda 2, dot, 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 all the way up to lambda n. That should look familiar. Isn't that just our second fun fact? When we multiply the lambdas, we get the determinant of our matrix. So now we're actually able to sort of prove that using this diagonalization procedure. Okay, so that's kind of handy as well. Okay, so by the way, maybe I should make one more. I guess I'll call this number 3. This is kind of a nice application here. If I want to take, let's say, the matrix A and raise it to a power. Let's say I want to do A to the K. The fact that we can diagonalize A, assuming we can diagonalize A, then we can substitute this in S d S inverse to the K. Right? Now, what does that look like? I'm actually going to write it out a little bit. This is going to be S d S inverse times S d S inverse dot, dot, dot times S d S inverse. We just have sort of K copies of S d S inverse times S d S inverse, S d S inverse over and over again. But here's the deal, guys. Remember how I was just saying a minute ago that you can't cancel the S and the S inverse unless they're right next to each other? Do you see in this expression that some of them are now right next to each other? You see the S inverse and the S right there in the middle? And then the next one and the next one? And then all the way along the line, there's an S inverse and an S right next to each other. You can cancel all of those interior S inverse S products. And what you'll be left with is an S and then D to the K and then S inverse. And that is not so hard to calculate, because when you take a diagonal matrix to a power, guys, is really easy to calculate, because you just power up the diagonal entries by whatever that K is. So if I have the matrix, 5007, maybe I'll write it down. I'm watching myself backwards in the camera. That's my problem right now. So if I had like 5007 and I want to raise it to any power whatsoever, right? If I had something like that, then the answer is, oh, it's just 5 to the K, 0, 0, and 7 to the K. It's just that simple. So it becomes really easy to do a calculation like that. Okay. I had also mentioned, on Tuesday one of the applications of this chapter. I talked about computer graphics and so on, but I also talked about this thing called a Markov process, where sort of every period of time, some change in the states of a system change. So maybe we have 2 professors teaching Math 250B, and the students are switching sections. Say once every day, a certain percentage of students go from this professor to this professor, and a certain percent go from this professor back to this professor, right? They're switching sections. This is called a Markov process. Once every day, there's a change in the configuration. Well, you can actually represent that change of configuration as a matrix. And if you want to know, well, how much has the configuration changed by the end of the semester? right? Now, every single day that you have this change of configuration, it's like multiplying by the matrix A, whatever this A is that's representing the system. So the end of the semester is, I don't know how many powers of A that would be, but it's a lot, right? There's a place where you want to be able to calculate a high power of a matrix to figure out, well, what will be the configuration, many iterations of this back and forth business down the line, okay? So if we were face to face and we had a lot of time, I would probably actually go through a full example with you of that. I don't think I'm going to right now, because I generally don't put it on a test, and it's not something that's in the mainstream. And given that we are already challenged enough as it is to just get through the core material that we really need to do, I think I'm going to let that go for the time being. Maybe I'll come back to it, you know, if there's extra time later on, but I think I'm going to let that go for right now. Okay, are there any questions at all on any of this diagonalization stuff? Oh, there is one more question that I forgot to address, and I should address it real fast. So let me go back to the example that we had done earlier. Do you remember the matrix? We had the matrix B. So this is just an example. Okay, so just really quickly, and then we're going to take a break in a minute. But let's write down this matrix B, 2, -5, 5, and then 0, 3, -1, and then 0, -1, 3. This matrix that we looked at earlier is diagonalizable. Let me remind you, we'll write down again what the key points were here. We had lambda equals 2, 2, and 4. And over here, for lambda equals 2, we got a basis of 1, 0, 0 and 0, 1, 1. And for lambda equals 4, I didn't really do it, but I told you to check it if you want to. You get a single basis vector, 5, -1, and 1. So you see, everybody's pulling their weight, right? Every eigenvalue is pulling its weight, and so everything is good to go. Okay, let's just write down the S and the D for this. Okay, so in this case, S is equal to, so what we are going to do, we're going to build a matrix S whose columns are these eigenvectors. And this was a point that I had wanted to make that I forgot to make earlier, which is, let's suppose that the person next to you, hopefully they're at least 6 feet away from you, but the person next to you has put the vectors into the columns in a different order. So I might choose to put them in the matrix S like this: 1, 0, 0, 0, 1, 1, 5, -1, 1, right? That could be my S. But you might be wondering, do you have to put them in that order? Could you put the 5, -1, 1 in the first column instead? Or do you have to put them in the columns in a certain way? The answer is, it doesn't matter. You can put the vectors into S however you like into the columns, in whatever order you want, as long as when you write down what D is, the diagonal matrix, that the lambdas are organized in the same order. Okay, so in this case, I would also have D to be the matrix. So in this case, it would be 2, 2, 4. We have zeros everywhere else, right? Sorry, let me write that out better. So what I'm trying to say, guys, is if they ask you to diagonalize a matrix and they want to know what's S and what's D, this is a correct answer, but it's not the only correct answer. Because somebody could switch the positions of these columns, and that's not wrong, as long as the positions of the lambdas over here is switched accordingly. Okay, so if you're checking your answer in the back of the book and your columns are shuffled differently than what the back of the book says, that's fine as long as your lambdas on your diagonal matrix D are shuffled in exactly the same accordance with that. Okay, so there's can be more than one right answer to this. Now, on the homework problems that you're going to do for Tuesday, listen up, because I'm going to save you from spending time doing something you don't need to do. There's going to be some homework problems in 7.3 that are going to say things like, decide if the matrix A is diagonalizable, and if it is, find an invertible matrix S and a diagonal matrix D such that S inverse AS equals D. That's what the homework question is going to say. However, the question is not going to say, find S inverse. Okay, so you can have this equation. In this case, it would be S inverse BS equals D for our example, right? This equation is the main equation involving diagonalization, but the homework problems are just going to say find S and find D. In other words, exactly the work that I've done right here. Okay, don't bother to find S inverse if you don't have to. Okay, yes, S does have an inverse, so we could find it, but for a 3x3 matrix, that's going to be a 10-minute job, right? We have to use the adjoint method or the Gauss-Jordan method, going back to chapter 3 or chapter 2 even. So we can avoid that in the homework problems that you're going to do for Tuesday. You don't have to find S inverse. You just have to find S and D. So, okay, now I think I've said everything I need to say about this section. Actually, this is kind of it for chapter 7, which is great. It wasn't that bad of a chapter. There was a semester where I actually had to miss classes for a while. So I made a bunch of videos. I think I'm going to probably put them on the website, and I'll link them for you. As long as you're understanding what I'm saying right now, you probably don't need to watch those videos because it's basically just this. But I'll put those up there too in case you guys want to look at them. Okay, let's do this. Let's take about, I don't know, maybe a 5 to 7 minute break right now. I just need a chance to grab a glass of water real quick. I'm up at high altitude, so just a quick little chance to rest my voice for a minute. While I'm taking the break, if you could look at the homework that's due today, and if you want to type any questions that you might have homework questions about into the Zoom group chat. When we come back from the break, I'll take a look at those with you. And then we're also going to work on a group work after we come back from the break. So I emailed you guys group work number 11. If you don't have it, it's all right. I'll write the questions on the board, but you might want to find that email. Maybe you printed it out, or at least you have it electronically on your screen, because those are some very good problems in that group work. So I'd like to do that also when we come back from our break. So let's take till about 1:10 to 1:15, somewhere in there. We'll see how everybody's doing. If people are ready in 5 minutes, we could start in 5 minutes, but we'll take a short break. Let me know what questions you have, and we'll be back in just a few minutes, okay? Thanks. All right, guys. This doesn't work quite as easily as when we're in the classroom because I can see if everybody's back and know that it's time to start. I can tell that most of you are still here, at least in the room, but hopefully you're somewhere within the sound of my voice. I think I'll go ahead and start looking at a couple of these problems from the homework, particularly the last two problems on the assignment are primarily theoretical problems. So, what we want to do is give a pretty short solution to these problems. They're not very computation heavy, so to speak. So let's look at this first one here, number 41. Suppose you have a square invertible matrix A. So A is invertible. It says, show that if lambda is an eigenvalue of A, then 1 over lambda is an eigenvalue of A inverse. The interesting thing about this is that you might be wondering, well, could lambda be equal to 0? Because if lambda was equal to 0, then 1 over lambda won't make sense. So the thing is, if you remember our little fun fact about the product of the lambdas being the determinant of your matrix. So this is not part of the solution. I just wanted to point something out to you here. If A is invertible, then this determinant is not 0, right? For an invertible matrix. And so that actually means that none of your lambdas could be 0, right? None of your lambdas can be 0. So it's a safe thing to talk about 1 over lambda on this problem. Okay, so I just wanted to point that out in case anybody was wondering about that. But the way to do this for the solution, the way to do this is to start with the most important equation in chapter 7, which is just the following. We have, of course, AV equals lambda V, right? So when you're doing theoretical problems about eigenvalues and eigenvectors, that equation in the box is almost always going to be really important, okay? Now, this matrix is assumed to be invertible, and that means that there is an A inverse that we can use. And if we want to show that 1 over lambda is an eigenvalue of A inverse, we're going to need to bring the A inverse into our solution somehow, okay? The trick to doing this is to actually multiply the box equation by the A inverse. But please do it on the left of both sides of the equal sign. It does not make sense to do something like this, right? You can't take a vector, which is a column, and multiply it by an n by n matrix. It doesn't even make sense as a multiplication to do something like that. So you want to be careful about how you're actually setting this up. So what I'm going to do is I'm going to left multiply by A inverse, okay? So then A inverse times A times V is equal to A inverse times lambda times V. So we're just literally left multiplying by A inverse on both sides of our equation. And A inverse times A is just the identity. So we can reduce that to V equals, on the right side, I'm going to put the lambda out in front. And then I have A inverse V. Lambda is just a number, right? So it's perfectly safe to pull a number out in front. It's just with vectors and matrices that we have to be extra careful. But in this case, there's no problem at all with just going ahead and putting the lambda out in front. And the only thing left to do now is to divide by lambda on both sides. Okay, so in other words, 1 over lambda times V is equal to A inverse times V. And guys, that right there is your boxed equation again, but with A inverse and 1 over lambda as your matrix and your eigenvalue. Okay, so that does it. That's the whole proof. That's the calculation. These are short write-ups. You know, they don't take that much to write them up. Are there any questions on that one? Okay, sounds like everybody's good. Let's look at 42. 42 has a few parts to it, so I might just get the first part started for you, and then I'll let you guys try the rest of it. But 42 involves 2 different matrices. Let me write it down. So on 42, we have A, which is n by n, and we have B, which is n by n, right? So we take a couple of matrices like this, and it says, assume that V is an eigenvector of A corresponding to lambda. Okay, so I'm just reading the question. Assume that, so I'm going to write it down here. By assumption, it says assume that V is an eigenvector of A corresponding to lambda. Well, that just means that AV equals lambda V. Right? All of that text that I just read reduces to that equation right there. AV equals lambda V. Okay, and then it says also V is also an eigenvector of B corresponding to eigenvalue mu. That little curly U symbol is just mu. So I'm going to write that here. B times V is equal to mu times V. So we have this assumption as well. Okay, so then what they're asking you to do in part A, I think I'm just going to do part A and then I'll let you guys try part B on your own. But part A just says prove that V is an eigenvector of the matrix AB. So we're going to look at the matrix A times B. And with this matrix, they want us to show that V is still an eigenvector. So what that means is that when I take this matrix and multiply it by V, I'm supposed to get some scalar multiple of V back again. Okay, guys, this problem does not involve using the characteristic equation or finding any null spaces or doing anything like that because we don't have the matrices in our hands. This is an abstract problem. So we can't really procedurally go through the process the way most of the problems that you'll be doing for next Tuesday are going to look. This one is just literally using the basic equation that we've already got in this box up here 2 times, right? So A, B, I would like to show that V is still an eigenvector of it. So I'm going to put the vector V next to it, and I'm going to see what happens. Well, I can see right away that there's a BV right there, and I already know what BV is right here. You see? The BV can just be replaced. So let's just do that. This is just A mu V. Okay. And mu is just a scalar, so I can pull that to the front. Mu is just a number, so I'll pull the mu out into the front of it, and then I just have mu times AV. But I also know what AV is. AV is just lambda V. So I get mu lambda V. And I can just kind of think of mu times lambda as my eigenvalue now, and I'm done, right? AB times the vector V is equal to mu lambda times V. That proves that V is just stretched by a scalar factor, which is in this case mu lambda, when you multiply by AB. So that's all you have to do. And part B is almost the same thing. I'll let you guys try that one out. Okay? Good enough so far? Matt, just a quick comment for you, because I'm not going to do number 6, but I see you have a quick question about it. On problem number 6, there's a 2x2 matrix that they gave you. And they're asking you to find the eigenvalues of that matrix. Now, of course, we know how to do that using the determinant of A minus lambda I, we could do that. But in this case, the other way that you can get the eigenvalues is they happen to give you the eigenvectors. Now, please understand, this is totally backwards from the way it usually works. Right? Usually, you don't know what the eigenvectors are at all, and you start first by finding the eigenvalues using the characteristic equation. So on problem number 6, it's a little backwards because they're handing you eigenvectors to begin with. So what you can do is you can just take the matrix A and multiply it by the vector, -2, 1. Of course, that needs to be written as a column. But just do that matrix multiplication. Take A times, V1, I guess it is, and see if it gets stretched by some lambda. Whatever that stretch factor lambda is, that's your eigenvalue. And you just have to do that with both of those vectors. So this is not normally the way you proceed to find eigenvectors, eigenvalues, and eigenspaces. But this was just more or less to have you practice a little bit the fact that you can take A times V and figure out if V was an eigenvector or not. Okay? Yeah, so that's how you do it. If you want, you can just use the characteristic equation too, because that's really the way you normally have to do it. But that's great. Okay. Just a reminder, guys, I'm going to be around in my office hour Zoom hours as well today, so you can catch me like after class in a little while, as well as later on tonight after my other class. I'll be around too. That's after 5:30. So feel free to, if you have any other questions, to drop in. This should be a short assignment. Like, I'm hoping that most of you probably shouldn't take more than like 1 to 2 pages at the absolute most to get that all done. Okay? All right, I'm gonna go ahead and erase this. And I wanna just say a quick word about a group work that, of course, we're not really able to do group work very easily at this stage of the game. But I want to look at these problems because they're pretty good problems. Let's look at group work number 11. Now, I've emailed this to you. If you don't have it in your email, of course, you'll be able to find it on my website again. And the solutions are also on my website for you to look at later. But for right now, I'll go ahead and write these problems on the board. Let's look at number 1. There's 2 parts here. It asks us to give an example of a matrix that is invertible but not diagonalizable. You see, the thing is that people think of invertible matrices as being a good thing, and people think of diagonalizable matrices as a good thing, but they're not the same thing at all. So this group work is intended to sort of get you to forget about the idea that invertible and diagonalizable are related, because they really are not. Okay, so we're being asked to give an example here. So what size matrix do you think would be good for an example? So we're going to give an example. What size do you think we maybe should use? Anybody have a thought about that when we're doing examples to show things? Yeah, 2 by 2, exactly. So we're going to try and do this with a 2 by 2 example, okay? Now, I had mentioned something to you on Tuesday about, the eigenvalues of a matrix when you're creating examples. Remember that when you have a triangular matrix, right? Triangular matrices are especially nice because the lambdas are just going down the main diagonal, right? So I'm going to make my example really nice by making it upper, I'm just going to make it upper triangular. So to make a matrix that's upper triangular, I have to put a 0 in the lower left corner, right? And so my lambdas are going to show up on the main diagonal. Now the thing is that if we want our matrix to be not diagonalizable, we have to have an eigenvalue that doesn't pull its weight. So this means that when I'm thinking about what I want my lambdas to be, which are these two numbers that we're going to write down here, they should be the same, right? We need to use the same number in both places, because that way we will get a repeat eigenvalue. So you can pick pretty much any number you want. I'm just going to pick 4 and 4. Just pick something like that. Okay? So even before I do anything else, I already know that my lambdas are 4 and 4. I actually also know that the determinant of this matrix is 16. This is invertible, right? So I'm not even done with this yet, but this is invertible. I'll put a check there. I know that this will be invertible no matter how I finish this matrix. And I have a repeat lambda. But here's the possible problem. The possible problem is that what if this eigenvalue still manages to pull its weight? I know it's repeated. Let's just put, we don't know what number to put here yet. I'm going to just put a little star there for the moment. Let's look at this eigenspace corresponding to lambda equals 4. So we're going to do the null space of what? Of the matrix we get when we subtract 4 from the main diagonal. My matrix is going to look like that. And the question is, how big is that null space? Is it going to give me 2 linearly independent eigenvectors or not? Remember that those eigenvectors come from busting out the variables, the free variables in this process of solving for this null space, right? When you solve for this null space, you circle your pivots, you then set up free variables for the unpivoted columns and solve it by back substitution, right? If that star right there was a 0, we would have no pivots in this matrix. And that would mean that we would have 2 free variables, and my lambda would pull its weight because it would give me 2 linearly independent eigenvectors out of those 2 free variables when I bust them out, right? So I don't want that. So in order to make my matrix not pull its weight, to make this eigenvalue not pull its weight, I need to choose a number for this star, any number I want, except I cannot choose 0. So as long as I don't choose 0, let's say I choose 1, now I have a pivot there. I only get 1 free variable, and lambda does not pull its weight. So this would be a good example right here for part A. Okay, great. Let's go ahead and look at part B. Are there any questions on that? Good enough? Okay, part B. Part B says, give an example. I'll just say ditto here, of a matrix that is diagonalizable, but not invertible. Okay, so in other words, we can reverse the process, right? We can say find something that's diagonalizable but not invertible. I'm trying to convince you that these two concepts have nothing to do with each other. You can be invertible but not diagonalizable. You can be diagonalizable but not invertible. There's not really any relationship. Again, I'm going to follow Caesar's advice and use a 2x2. And I'm going to, again, try to get away with an upper triangular matrix. Again, for creating examples, Triangular matrices are great in chapter 7 because the lambdas go straight down the main diagonal, just to reiterate that. Okay? So one way to absolutely guarantee that my matrix will be diagonalizable, remember that means not defective, would be to just choose different numbers on the main diagonal, right? Different numbers. But I don't want the matrix to be invertible this time. Can somebody propose what numbers I should maybe 2 different numbers that I can put on the main diagonal here? Could I put like 3 and 6? Remember, guys, the determinant of the matrix is going to be the product of these two, right? And you want the determinant, if this matrix is not invertible, you want this determinant to be 0. So Caesar, you're absolutely right. We definitely want to use a 0 here somewhere. But then let's choose some other number. I don't care what number you pick. Pick some other number, because that way I know that this, see, this is triangular. I'll put a little star up here again in the upper right corner. This is an upper triangular matrix. My lambdas are 0 and 5. There's no repeats, right? So that means that everybody's going to pull their weight. It's going to be non-defective. It's going to be diagonalizable. But obviously, this matrix has a determinant of 0. It's not invertible. So here we have a nice example of a matrix that's diagonalizable, but not invertible. Okay, so you can work it kind of both ways using these little 2x2 examples. It's really good. Okay, let's do one more thing here. I'm going to go to problem 2b. 2a is really easy, so I'm not gonna worry about that. But 2b says, let me pull it up. True or false? True or false? If A and B are diagonalizable, then so is A plus B. Okay, let's try this. So problem 2a is really easy. I'll skip that one. You guys can look at it later, but this is an interesting one. If we take 2 diagonalizable matrices and we add them together, will the result still have to be diagonalizable? It's a good little thing for us to think about for a second. Okay. Well, what if your matrix A had 2 different lambdas and your matrix B had 2 different lambdas, but then you add the matrices together and the new matrix somehow now has the same lambdas? Could that happen? Let's just try this. Let's just try this. Let's take a matrix. I'm gonna make this really easy on myself. I'm going to make all of my matrices triangular. So this is one of the big themes from this group work, guys. If I ask you to create examples that have to do with diagonalizable matrices, defective, non-defective, use 2x2 matrices that are triangular, because the lambdas in this case are just right down the main diagonal. Okay, so I'm going to make a matrix. This first one is going to be A. And I'm just going to make sure that it has 2 different lambdas. So I'll just use a 1 and a 2 there, right? And I'm not going to fill in the top right corner quite yet. I'll come back to that. The second matrix, I'm going to do the same thing. I'm going to make sure that I use 2 different lambdas here. But let's think ahead. Would it be possible to choose 2 different numbers here and then have the lambdas become the same over here? I bet that could happen, couldn't it? If we just choose our numbers carefully. What if I chose something like, I don't know, 6 and 5? Right? By the way, this is not the only answer, of course, but think about the concept of it. What happens when you add these matrices together? You get the same lambda. Now, same lambda isn't necessarily a problem. Okay, people make this mistake. They think, oh, there's a repeated eigenvalue, so it's defective. Not necessarily. It's only defective if this eigenvalue doesn't pull its weight. So to make sure that this, I claim that this is a false statement. I already have a diagonalizable matrix here for sure. I have a diagonalizable matrix here for sure. But this matrix, if I just put a 1 or any number other than 0 there, this 7 will not pull its weight. Okay, and now I can just finish the rest of the matrices here. I could put a 1 and a 0, for example, right, just to make it add up, right? And there you go. So A plus B is not diagonalizable, even though both A and B are. So this is a good example of something that is false. Okay, so we just did 3 little sort of mini problems to practice this concept of creating examples to show diagonalizable or not diagonalizable. Okay. Any questions on any of the problems from that group work that we just looked at right there? Okay. If not, we have only about 10 minutes left, but I'm going to try and use those 10 minutes if it's okay, because chapter 8, which is what we're going to start right now, you know, it takes a little while to kind of get into the nuts and bolts of it. And if I wait till Tuesday and try to cover everything on Tuesday, I will have a hard time keeping up with our schedule. So let's just take 10 minutes and we're going to completely change gears. I promise that this last part of our class will be really pretty easy, just kind of introducing some notation and getting started so that we can come in on Tuesday next week ready to go. So chapter 8, getting back to our notes again. I'm sorry, I'm sure you're all shuffling your group works and your notes and everything in the homework. But back to our notes for just a few minutes to finish up today. Chapter 8 is called Linear Differential Equations of order n. So at long last, for those of you who have not been big fans of linear algebra and you liked the differential equations that we did way back in, I guess, January, well, we're finally going back to differential equations. Differential equations of, that says of, I see there's a bit of a glare on my board there. Linear differential equations of order n, okay? So let me just start with a little bit of notation. By the way, we are going to see the linear algebra coming back almost immediately. So it's not very far away at any point from here on out. So I'm going to sometimes be using capital I to just denote an interval. This is just an interval on the real line. And so that could be the whole real numbers. That could be minus infinity to infinity, potentially. And then I'm going to use this notation here, C super 0 of I. This just means continuous functions. This is just the set of continuous functions on I. So we can talk about the continuous functions on that interval. And then I have C super 1 of I. This is going to denote the differentiable functions on I. And so on. I can put a C super K of I. So it's a C with a K as like a superscript. And this just means K times differentiable. I'll just say diffable here. All of this is just background notation. It's actually not that important for what we're going to do, but we're just talking about like how many times can we take derivatives of our functions. All of these sets here, these are just like calculus functions, and it's just, these are actually vector spaces. These are vector spaces. They're closed under addition and they're closed under scalar multiplication. But I'm not going to dwell too much on that. Instead, what I want to do is I want to give you a very important definition. This is maybe also, I could consider this notation. But I'm going to define capital D, which is going to go from C super K of I to C super K minus 1 of I via, so I'm going to create a function right now, okay? This is really just notation. D takes a function f and it just takes its derivative. So D of f is just f prime, okay? And more generally, if I see D to the, let's say, the kth power of f, you probably know what that's going to mean. That's just D of D of D of D, k times. Well, you end up with k derivatives of f if you do that, right? Okay. The beautiful thing about this is, recall, so this is actually something, this is a concept that we've seen recently. This is a linear transformation, right? Derivatives respect addition and they respect scalar multiplication. You can differentiate term by term and you can pull constants out when you take derivatives. So D is linear. Okay, D is a linear transformation. So I usually just say D is linear. That's what that means. And so the great thing about that then is that I can write a linear differential equation of order n, which is what we're going to be studying in this next week or so. I can write it using this D notation. And it's just much cleaner than what we would have had before. Let me write down, let me remind you what we used to write, how we used to write down this nth order linear differential equation. So if I have an nth order linear differential equation, how does it look when we write it down on paper? Well, we did this way back at the beginning of the semester. You know, you have like a0 of x times y to the n derivatives, right? And then plus a1 of x times y to the n minus 1 derivatives, and so on, right? And then finally you get to the last term here, which is an of x times y. And then it was equal to capital F. We wrote that down like in January, like the first 2 days of the semester. That is the form of an nth order linear differential equation. The unknown function is y. And you see that each of the terms on the left has one of the derivatives of y in it. And the coefficients in front of each of those terms is some function of x, right? And then the right-hand side could be anything, f of x, whatever it might be, okay? This is how we used to write our differential equation. But I'm going to write it differently now. I'm going to write this differently. So I'm going to rewrite this with the D notation. I'm going to rewrite it using our new D notation at the bottom of my board. Okay, and here's what it is. Basically, I'm going to suppress the x's here. I'm just going to write a naught times d to the n plus a1 times d to the n minus 1 plus dot, 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 plus an. All of that in parentheses. And this is of y equals capital F. So this is just a nice, shorter notation. It's cleaner. It's less cumbersome when we write it like that. So you're literally like distributing these terms to the y, right? So the first term, a naught times n derivatives of y. And then the second term, a1 times n minus 1 derivatives of y. So each term gets applied to y, right? And this whole thing right here in the first set of parentheses, this is a combination of different powers of d, and d was linear. Respects addition and scalar multiplication. Capital F is just some function, by the way. On the right-hand side, I should probably say of x here. So just think of whatever calculus function you want. It could be cosine of x. It could be e to the 3x times ln of x, right? Any function that you could think of for now. But the crucial stuff is happening on the left side in this bracketed expression here. This is linear. This is what is called a linear operator. It operates on y by taking various derivatives of y. It's often just abbreviated with L. It's often just abbreviated L. So we have an even more shorthand version. We have an even more shorthand version of this equation. So in shorthand, L of y equals F. So that's basically it. And this is just a very brief way of writing your differential equation. So I'll wrap this up. What is our goal going to be? Our goal is going to be to solve for y. As it's always been, right? Whenever we have a differential equation, our goal is always to just figure out how to solve for y. We're first going to learn how to do that in the case when f is 0. So on Tuesday, most of Tuesday, we're going to be looking at the situation where capital F is just 0. And then probably by Thursday of next week, I'll start to address, well, what do we do if the capital F is not 0? See, one thing you probably already notice is if the F is a 0 here, then what we're really solving for is the kernel of L. Do you remember that concept? The kernel of a linear transformation? The kernel of L is those functions that spit out 0 on the right-hand side. So on Tuesday, we're going to look at a lot of examples. We're going to find the kernel of some of these differential operators that I've written down. I know I didn't really do any examples today. I just had to get the notation down. On Tuesday, I'm going to write that notation on my recap at the beginning, and then we're going to dive into some practice and into some examples, and we're going to start actually learning how to solve these nth order linear differential equations. It's a beautiful theory, and I'm looking forward to sharing it with you. That's all I've got for today, guys. I really appreciate your hard work and your attention in spite of all of the craziness. If you missed anything or you need to refresh your memory about anything, by all means, I'm going to put this recording on my website in just a few minutes, and it'll be there from now till the end of the semester. So any questions before we go today, guys? Okay, and I'm going to move over to my office hours room, so you can also pop over there if there are any questions that anybody has. But thank you for your attention. It's great seeing you all. Stay safe, be well, and we'll meet up again next week at 12 o'clock. So take care. Have a great weekend, everybody. I'm going to go ahead. Bye-bye. I'm going to go ahead and end the meeting now. So see if I can do this. All right.